All right. So now it is past 12. So it is good afternoon from here and good morning to all the colleagues in France. So we'll get started, and I request Aritra to make a brief presentation of the work. Let me also introduce Professor K.P. Ray, who is the examiner, and Professor Cedric Quendo, who is the co-supervisor for this project.
Okay. So I'm just sharing the presentation.
Yes, Aritra, we can see it.
Okay. Okay. So with your permission, I start. Just a minute. I think wrong slide. Okay. So hello everybody to the thesis defense program. So today the title of my talk is Design of Compact Antennas with Meta Surface for Wideband and Wireless Application. So here is the just a minute. Yeah. So here is the outline. I shall briefly discuss the objective and briefly discuss the literature. Then I shall go chapter wise. So in the first part, we studied a reference spiral antenna and its effect of varying the antenna height above a flat metallic conductor. And then we proposed a modified conical profile below the antenna. In the second part, we have investigated the design of compact antennas by placing it above a flat metallic plane, but by using different absorbing techniques. So in the first absorbing technique, we used a hybrid absorbing technique. In the second, we used a metasurface based absorbing technique. After that, we tried to tilt the main beam of the compact antenna using two different techniques. First, using a dielectric lens, and second one, using a metasurface. In the last part, I have addressed a wireless link design by using a digitally reconfigurable metasurface based modulator. So as it's already clear that we are using metasurface for two different applications. One is for wideband applications, which is often used especially for electronic warfare. And second one is for a spatial modulation to communicate in a multipath environment. So for the first part, we have used spiral antennas. Why? Because spiral antenna is one of the most widely used wideband antennas for electronic warfare. So we investigated different performance of the spiral by placing it above different type of metallic planes by using different type of absorbers with the spiral. In the second part, we have designed a digitally reconfigurable metasurface to implement a modulation technique called media-based modulation. So here we have performed numerical analysis, then have performed several experiments to make different comparison between different scattering environments. So in the literature, a metasurface is there now. It's almost for 2 decades now, and it is used from the domain of mechanics till optics. So we are in middle, we are somewhere in microwave. And here for antennas, it is often used to miniaturize the geometry, to improve the gain, to make multiple antenna beams, to tilt the beam, even to implement multi-user communication systems. Similarly, in spiral antenna is now here, it's almost 7 decades. So it is widely used for different commercial applications, but still people are working to develop it further, to design it according to their application. So let's go now into the topic. This is the reference spiral antenna. It is a dual arm 8-turn Archimedean spiral antenna, which we considered so that it can work from 2 to 18 gigahertz. Now for spiral antenna, the maximum perimeter corresponds or determines the lowest frequency, and the minimum dimension determines the highest frequency of operation for the antenna. Here at the S11 of the freestanding spiral antenna, over 2 to 18 gigahertz, we have observed the response, and the S11 is less than minus 10 dB throughout the band. For the gain, we have plotted the RHCP gain. The gain varies between 3.5 to 7, 3.5 to 6 dBIC, and the axial ratio is circular, means axial ratio is less than 3. Polarization is circular after 3 gigahertz. as I said earlier, it radiates through different active regions or annular rings, and the perimeter of these annular rings are equal to the free space wavelength of the working frequency. So obviously, if the frequency increases, the perimeter of the ring will become small. And the spiral antenna, actually in a freestanding mode, radiates on both sides of its axis. But for practical application, we have to keep it close to a metallic plane, such as a body of an aircraft. And by doing so, we can make the radiation unidirectional. But when we place it close to a flat metallic plane, we see different problems at low frequency as well as high frequency. Now, what happens when we feed the spiral antenna? The current goes from inside to the outside of the spiral. When we place the spiral in front of a flat conductor or very close to a conductor, the radiation efficiency at the low frequency reduces. When the radiation efficiency reduces, the low frequency electromagnetic waves doesn't radiate well from the antenna. So they basically they are reflected at the antenna edge and comes back to the antenna feed and degrades the low frequency axial ratio as well as the impedance of the antenna. So what we can do, we can remove this residual current from the edge of the spiral by using an absorber. In the picture, you can see when we have a flat conductor at 5 mm and we have an absorber, we have almost a similar performance like the freestanding antenna, but obviously with unidirectional radiation. In the next investigation, we varied the height of the antenna above a flat metallic plane. Now let us look into this picture closely. If we look into the axial ratio response, we don't see much effect of height variation between 6 to 18 gigahertz. But when we see the effects between 2 to 6 gigahertz, what we can see, if we increase the antenna height, the axial ratio at 2 gigahertz improves. Similarly, in the gain, if we look between 2 to 6 gigahertz, if we increase the antenna height, the gain between 2 to 6 gigahertz improves. But if we keep increasing the antenna height, we can see a lot of ripples in the frequency response in between 6 to 18 gigahertz. These ripples are due to the destructive interference between the antenna field and the ground reflected field. So with that idea, what we understood is if we keep the antenna close to a ground plane, we have a good frequency response at high frequency. Whereas if we keep it away from the ground plane, we get a good response in the low frequency. So to combine these two effects, we have investigated a conical geometry where the height is less near the high frequency region and height is more near the low frequency region. Now, if we look into the table and into the plot, we can see the gain at 2 gigahertz is significantly low when the height is small, whereas the gain can be increased if we increase the height. On the other hand, if we use a conical geometry, the gain is somewhat close to the 12 mm flat plane. But if we look into the gain variation, then we understand what is the usefulness of this structure. For a flat 5 mm plane, the variation between 10 to 18 gigahertz is very less, whereas when we have an antenna height of 12 mm, the gain variation is very high between 10 to 18 gigahertz. But when we use a conical geometry, it is comparatively less. So with this idea, we just modified the geometry, what we called a modified conical profile or a truncated conical profile, which is a combination of a flat and a conical ground plane. The flat region is placed only H1 below the spiral and it has a radius of R1. In the simulation, we have shown that if we optimize the result by varying R1, we can restrict the gain variation within 1.1 dB in between 6 to 18 gigahertz or 10 to 18 gigahertz. In other words, it's possible to make the antenna response or the gain response significantly flat in the high frequency by optimizing the R1. So after that, after optimizing the geometry, we have fabricated it. We have fabricated using 3D printing and covered the top of the dielectric layer with a metallic tape to implement the metallic ground plane. We have also used absorbers and balance. When we measured the geometry, we observe an S11 less than 10 dB throughout the band. We have an axial ratio less than 3 dB almost throughout the band. Here we also observe the effects of balun and no balun in the simulation. We plotted the RACP and LACP gains are shown here. What we observed is we have a maximum gain of 8.6 dB IC, and the gain variation is restricted in between 2.8 dB from 10 to 18 gigahertz. So this was a significant improvement. We have also plotted the radiation patterns for the two principal planes at different frequencies, where we can see the good RACP responses over wide angular beam width. So here is the conclusion of this chapter. Is first we investigated a reference parallel antenna in freestanding configuration. Then we varied the antenna height to see the effects at high frequency and low frequency. Then we investigated a conical geometry and modified the conical geometry using a truncated conical geometry, where we achieved good antenna gain and flat frequency response. Then we realized that it is difficult to always make a non-planar geometry. So we thought of using a flat ground plane, as you can see in this picture, but we placed the antenna very close to the ground plane. We have placed it only 5 mm. So 5 mm is lambda by 30 at 2 gigahertz. So when we do so, I have already said that we need an absorber to improve the low frequency responses. So here I have studied the effect of absorbing material with the spiral. Here I have defined one parameter RABS, which is the inner radius of the dielectric ring. What we saw, if we reduce the inner radius, the axial ratio below 6 gigahertz can be improved. But at the same time, it degrades the antenna gain at 2 gigahertz. So in other words, using dielectric material, we can improve the low frequency axial ratio by sacrificing the antenna gain. Then we investigated a lumped resistor configuration as an observer. Here what we have observed is it is possible to improve the low frequency axial ratio without affecting the antenna gain. So with this idea, we have proposed a technique called a hybrid absorbing technique, where we have used both of them together and optimized the parameters independently. By doing so, we have achieved this performance. Here I have plotted the axial ratio and gain for only absorber, only resistor, and with our proposed technique. What we can see, only absorber and only resistor does not give us good axial ratio in low frequency, whereas when we use both of them with optimum parameters, we can get a good axial ratio throughout the band. And most interestingly, the RHCP gain throughout the band remains unaffected. So in this way, we have improved the absorbing technique over other classical techniques. But this system has a limitation. Why? When we were successful for 2 to 18 gigahertz, we tried to extend the frequency band from 1 to 18 gigahertz. So first thing what we did, we increased the number of turns in the spiral so that it works from 1 gigahertz. And then we tried to optimize that spiral with this technique. What we observed is it is difficult either to optimize or it is not possible to optimize this proposed technique below 2 gigahertz. So we realized that we have to improve the absorbing technique further to work from 1 gigahertz. With that idea, we have designed a wideband metasurface. So here is the schematic of the wideband metasurface, which consists of concentric rings, metallic rings, and lump resistors in between. And the metasurface is printed on below the antenna substrate. So the same substrate is holding the antenna as well as the metasurface. And this metasurface and antenna, we have kept only 5 mm above a flat metallic cavity. So you can understand now 5 mm for 1 gigahertz is lambda by 60. So our cavity depth is now significantly small. After so we have also characterized the unit cell by placing it below a 3-wire differential line. So this 3-wire differential line replicates the performance of a spiral antenna. What we have observed is if we vary the length, width, and the resistor of the unit cell, we can achieve approximately 20 to 30% of absorption using a single unit cell. And obviously, if we place multiple unit cell, this absorptivity can be significantly improved. Here is the electric field plot at 6 gigahertz with unit cell and without unit cell. Clearly, we can see the absorption of the unit cell throughout the line. After that, we place the unit cell below the antenna and further optimize the geometry. That means we optimize the axial ratio of the overall geometry by varying the outer radius and the number of patches per ring. So in this optimization, our target was to select the dimensions which will give us an axial ratio less than 3 dB from 1 to 18 gigahertz. So accordingly, we selected the parameters from here. Now comes the most important observation about the proposed geometry. What we did for a fair comparison with a conventional absorbing material, we compared the performance of our proposed system with the system of a spiral antenna with an absorbing material. What we can see, the red curve in axial ratio, which is a metasurface absorber, below 2 gigahertz, our system gives an axial ratio which is less than 3 dB. Whereas when you use a conventional absorbing material of same dimension, it does not give an axial ratio less than 3 dB. At the same time, if we look into the RSCP gain at 1 gigahertz, our structure gives a better gain. So the bottom line is our proposed metasurface can give us a very good axial ratio from 1 to 18 gigahertz with a better low frequency antenna gain. So after all these studies are done, we have fabricated the geometry. As you can see, it's showing the cross section of the structure, showing the balun, cover of balun. Even we have made a flush mounting. And then we have measured it inside a chamber. In the measurement, we achieved good S11 throughout 1 to 18 gigahertz. We had a circular polarization response from 1.1 to 5 gigahertz. We measured the antenna gain, where we achieved a maximum gain of 8.7 dBIC. Here are the radiation patterns for different frequencies for different principal planes, where we can say that the RSCP radiation is present over a wide angular beam width. So from the summary, we can say here we have investigated the effects of commercial absorbing material and lump resistors and absorber, then have proposed a hybrid absorbing technique and designed a 2 to 18 gigahertz spiral antenna with a cavity depth of lambda by 30. Then we find out the problems of that structure and replace the absorbing material with a metasurface. When we did so, we designed a 1 to 18 gigahertz spiral antenna, which has a maximum gain of 8.7 dBIC with a cavity depth of lambda by 60. So that was all about designing a compact spiral antenna. Our next target was to use the compact spiral antenna and to tilt its beam at a constant angle. So if I just show you the concept, our idea was to cover half of the antenna aperture with a sort of lens so that there is a field imbalance across the antenna aperture and our radiation pattern tilts at an angle theta t. Now tilting the radiation pattern is not a problem. The problem is to maintain the tilt angle over a wide frequency range, and that was the challenge for us. So to do so, we have made a lens which is made of a partially absorbing dielectric material, or PADM. So this material has both real and imaginary permittivities. So in the first investigation, what we did, we used a semicircular flat lens. Okay, so this lens has a constant thickness of H1. And then we have summarized the tilt response, the theta t, over a wide frequency range like 3.5 to 6 gigahertz. What we have observed that if we increase the height of the lens, the tilt angle increases. But we wanted to quantify this tilt angle. That is why we have defined. First one is the average tilt angle over the frequency range. Second one is more important, which is the standard deviation of the tilt angle. If we have a small standard deviation, that means the average tilt angle does not move much. If we have a higher standard deviation, that means the tilt angle is varying very fast with frequency. So what we have observed here with the flat lens, if we increase the lens thickness, the average tilt angle increases. At the same time, the standard deviation increases, which we do not want. And at the same time, the maximum antenna gain reduces, which also we don't want. So we try to understand the effect of the real and imaginary parts separately so that we can control these parameters independently. In the left part, we have varied the real part by setting the imaginary part to 0. What we have observed is by changing the real part, we can significantly increase the average tilt angle, but at the same time, the standard deviation also increases. So it is undesirable. In the left part of this, in the right part of the table, we have fixed the real part and increased the imaginary part. When we did so, we increased the average tilt angle, but the good thing is that theta SD is small. So from this study, we can say that the real part of the permittivity is important to get a good tilt angle, whereas the imaginary part is important to maintain the tilt angle over a wide frequency band. So after this study, we have proposed a lens. So this was the type of lens that we have designed. It is a semicircular lens divided into 9 sections. The heights in the middle section are maximum, and the height reduces linearly from both sides of in the phi axis. Now in each section we have set 4 different heights, H1, H2, H3, H4 at 4 different radial locations. Okay, now our target was to investigate what happens to the frequency response if we change this H1, H2, H3, and H4 independently. So for that, we have first varied the H1, and by varying the H1, we do not see much effect in the tilt response of the antenna. All the responses almost overlap with each other. When we vary the H2, we can see there is a variation between 3.5 to 4.75 gigahertz. When we vary the H3, we can see there is a high variation between 4.5 and 5.5 gigahertz. And similarly, when we vary H4, we see significant variation between 5.5 to 6 gigahertz. So the bottom line is, it is possible to independently change the height of the lens at different radial locations and change this tilt angle over different frequency bands. So after that, we have optimized the geometry and fabricated it. This is a 3D printed lens, and this is the measurement setup. When we measured it inside the anechoic chamber, we achieved S11 less than minus 10 dB from 3.5 to 6 gigahertz. And we achieved a maximum RSCP gain of 3.17 dBIC. These are the tilt responses. The radiation patterns for different frequencies is tilted, and we have measured an average tilt angle of approximately 17 degrees. But in this geometry, there is a problem. The problem is when we place a dielectric lens above a spiral antenna, it is no more a planar geometry. Okay, so we thought of why don't we replace the same material and place it inside the cavity so that the system becomes plane, and then replace the same material using a meta surface. That was the idea. So for that, what we saw that for both cases, if we place a dielectric material above or dielectric material below, for both cases, we can achieve a tilted beam at different frequencies. For one frequency, we have shown here. When we implemented in a meta surface, this was the geometry that we used. So this is another meta surface, which consists of metallic plates and lump resistors. Now, this metallic plates actually introduces a capacitive effect with the spiral, so which is similar to the real part of permittivity. And there are SMD resistors, so which is producing the loss or the imaginary part of permittivity or material properties. So to characterize the unit cell, we saw that this material or this unit cell poses both real and imaginary part of material properties for mu, epsilon, and for the refractive index. After that, we tried to optimize the geometry by varying the angular length, inner radius, outer radius, number of patches, and the resistor value to optimize the geometry. Now, optimize the geometry means we selected those parameters for which our theta average was high, means the average tilt angle was high, but the theta SD was low. So for those cases, we have selected these parameters and we have fabricated this geometry. As you can see, the meta surface, which is printed below the antenna substrate, and a cavity depth of only 5 mm is used. We measured the structure inside an anechoic chamber where we have observed S11 less than minus 10 dB from 3 to 6 gigahertz. This time we have a better RHCP gain than the previous technique. Now we have a 6.3 dBIC of RHCP gain. We also plotted the axial ratio, which was almost less than 3 dB throughout the band. These are the tilted beams at different frequencies. And when we measured the tilt angle, we achieved a maximum tilt of 28 degrees. So this is also more than the previous structure. The average tilt was 23 degrees. So in the summary of this chapter, our target was to tilt the antenna beam, means the beam of a spiral antenna at a fixed angle over the entire frequency band. For that, in the first part, we have designed a PADM lens. We have fabricated and tested the lens where we have achieved a average tilt angle of 17 degrees with a gain of 3 dBIC or 3.17 dBIC. Then we realized the problems of this structure and replaced the same lens using a meta surface. By using a meta surface, we have achieved a higher tilt angle, a higher antenna gain, and over slightly higher frequency band. So this was all about the work in the wideband case. Now comes to the last chapter, which is use of a digitally reconfigurable meta surface for media-based modulation. Now let's take 1 minute to understand the concept of media-based modulation. Most of us know different multi-antenna system like SSK. So in SSK or space shift king, when we have to transmit a single beat means 2 symbols, 1 and 0. We need 2 different antennas. If we want to transmit 2 beats, so we have to transmit 4 symbols and we need 4 antennas. So if we want to transmit 8 bits, in that case, we have 256 symbols and we need 256 antennas. So to simplify the geometric dimension or the size of 256 antenna, an intelligent single antenna solution is proposed. So this idea was there and it was proposed by the theoretician already, where they use a single antenna instead of 256 or more antennas and then place a reconfigurable screen in front of the antenna. Now what happens when they switch the unit cell of the reconfigurable screen, automatically in the far field, the magnitude and phases changes. Now this change in magnitude and phases are actually interpreted as data bits, like in a multi-antenna system. So we tried to implement this reconfigurable screen by using this unit cell. This unit cell consists of a meander line geometry, and the overall dimension is lambda by 7.5 in both length and width. And we use a single pin diode in the unit cell. Now let's look at the S21, means the transmission characteristics of this unit cell. When we turn the diode off, the transmission, the S21 at 4 gigahertz is minus 1.5 dB. Whereas when we turn on the diode, the transmission at 4 gigahertz falls to minus 20 dB. So it is as if like we turn on and turn off the diode and the transmission characteristic of the unit cell changes between on and off cases. So this is like an electromagnetic window, which is once open and once closed, depending upon the state of the diode. So to work at 4 gigahertz, we also designed a rectangular patch antenna, and in simulation, we achieved good S11 for the antenna. After that, we have designed an array, an 8 by 8 array, and has placed it in front of the antenna. So here, the array dimension as well as the gap between the antenna and array are numerically optimized. Here we have used an 8 by 8 array. And for simplicity and for sufficiency, what we did, we used a single control line for each column. So we have 8 columns and we have used 8 control lines. So if we have 8 control lines, we can get 2 to the power 8 or 256 switching combination. Now in simulation, we have recorded these 256 radiation patterns, both in magnitude and phase. What you can see is by switching the metasurface in front of the antenna, it is possible to get significant variation in the far field response of the antenna, both in magnitude as well as in phase. The magnitude and phase can be equivalently represented using a constellation diagram or scatter plot, like magnitude sine theta, magnitude cos theta, these two components. And if we just look at one of them, what we can see, we have a big set of data or big set of points. Now a user who wants to communicate can select 2 or 4 or 8 symbols out of any constellation and can communicate between each other. So once this simulation study was done, we have fabricated the geometry. Here is the current driver circuit. The current driver circuit drives the high current, which is required to turn on the diodes. Then we have set up a complete experimental setup in which we have written a Python interface which generates the symbol. Then the symbol is decoded, and once it is decoded into 8-bit binary, the metasurface is set to that state. Once the metasurface is set, then the far field S21 is recorded by the VNA, and this recorded data is then saved into the Python interface. So this cycle continues as long as we want to communicate in a wireless link. So once the hardware is prepared, we started doing experiments. The purpose of our experiment was to investigate the effect of scattering. So in the first set of experiment, we did a comparison between a scatter-free and a scattering environment. We all know that scatter-free environment is typically inside an anechoic chamber. So we performed an experiment inside the anechoic chamber and outside the anechoic chamber. And here what we did, we changed the distance between the transmitter, DRM is the proposed modulator, and horn antenna. We changed the distance between the transmitter and receiver by a multiple of lambda by 4 on 90 degree. What we saw, for each distance, we have cluster of constellation points in a scatter-free region. And most importantly, the change of lambda by 4 is reflected as a change of 90-degree phase shift inside a scatter-free region. So if we don't have any scattering, the change in distance is properly reflected as a change in phase. On the other hand, if we carry out the same experiment outside an anechoic chamber, we have scatterers. And when we have scatterers, the change in distance does not reflect in a change in phase properly. But for our practical usages, we cannot communicate inside a chamber. We have to go outside a chamber. So we carried out more experiments outside the chamber in line of sight and non-line of sight configurations. So this is the schematic of the experimental setup that we set in our laboratory. And here are the 2 line of sight and 2 non-line of sight configurations has been shown. These are the photographs of these 4 configurations. Then let's see the results one by one. So we have 4 cases, line of sight 1, 2, non-line of sight 1, 2. For all these cases, we have first recorded certain 64 symbols. For all cases, we have recorded 64 symbols. Now from each constellation, we have selected only 4 symbols. This selection was done by using a Euclidean distance-based technique. In the next stage, what we did, we plotted the bit error rate for these 4 cases. What is interesting to see here, if there is line of sight configurations, the bit error rate actually overlaps because there is a direct path between the transmitter and receiver. In the non-line of sight, there is no direct path. So all the communication happens through deflection. What we observed is very much interesting. Is in non-line of sight, we have a better bit error rate. So that means we are just utilizing the scattering present in the environment and are improving the bit error rate. So it is like we are just using the multipaths and are transmitting the same data using a less signal power. So this was actually predicted by the theoretician who worked on MBM, And through experiments, we have shown that it is possible to achieve a better bit error rate only by communicating in a non-line of sight scenario. In the next slide, it is to demonstrate the possibility of multi-user communication. So for that, we have set 3 non-line of sight configurations in LOS 3, 4, and 5. And we have collected a lot of symbols. So let's just see one by one. If we look into the C33, so C33 is the constellation point for NLOS 3. And we selected 4 symbols from that. And then plotted the same symbols for NLOS 4 constellation and NLOS 5 constellation. What we can see for the first row, the best symbols for NLOS 3 user are not the best symbols for NLOS 4 and 5. Similarly, in the second row, we can see C44. C44 means the best 4 symbols which are selected from the constellation of NLOS 4. When we plot the same symbols for 3 and 5, we see that the best symbols for the NLOS 4 are not the best for 3 and 5. So the bottom line is, even if there are multiple users sitting at different locations, different user will use different code book or different symbols to communicate. And most importantly, no user can know about the constellation of his neighbor, because no user sitting at one place will know about the multipath component of the user. So this is how we try to demonstrate a possibility of multi-user of a multi-user system where a single DRM can communicate to multiple users simultaneously or in a time division multiplexing manner. After that, we have collected a lot of symbols. So we have collected 14,000 symbols by recording the data, 256 symbol for each, and we did the experiment for 58 non-line of sight scenarios. The target was to make a big constellation and then to see what is the statistics of the symbols. Here we have observed something really interesting, but we do not have much conclusions based on this. The interesting thing is we have conducted experiments in scattering environment, which is not Gaussian. But when we made a very big constellation and see the distribution of this constellation, we find it to be Gaussian. So it is as if, since we are using a very big constellation, a non-Gaussian channel is behaving like a Gaussian channel. So we do not have much conclusion on this behavior, but this was one of the observation from our experiments. Our group is working on this technique to understand why this kind of non-Gaussian to Gaussian kind of conversion is happening and how we can quantify the performance of the technique in a better way. So this was the end of our experiments. Then we tried to set up a wireless link where we transmit and receive the data. So you can see the photograph of the Python interface. So whatever we transmitted, we also received back correctly without any error. So that was all about the work. The conclusion is that first, we have investigated a freestanding antenna for 218 gigahertz. Then we investigated the antenna height and then investigated a conical geometry and a modified conical geometry, where we have achieved a very flat response with a cavity depth of lambda by 12.5. In the next part, we reduced the cavity depth to lambda by 30. We investigated the effects of absorbing material and lump resistor and proposed a hybrid absorbing technique. In this technique, we have a good circular polarization over 2 to 18 gigahertz without sacrificing the antenna gain. Then we reduce the cavity depth further by increasing the frequency range. So this time we are working from 1 to 18 gigahertz. So the cavity depth is now lambda by 60. To work in such a configuration, we have proposed a wideband metasurface. And using the metasurface, we have shown that the proposed geometry actually can work better than the spiral antenna with a commercial absorber. In the next part, we have investigated tilted beam spiral antennas, first using a PADM lens, which is a printable partially absorbing dielectric material lens. In this technique, we have achieved an average field angle of approximately 17 degrees. But we have also realized that this is not a planar configuration. So to make this configuration planar, we replace the geometry using a meta surface below the antenna. By doing so, we increase the average tilt angle as well as we improve the antenna gain over slightly wider frequency band. In the last part, we have investigated a digitally reconfigurable meta surface to implement a modulation technique called media-based modulation. So here we have performed different experiments to study the effects of multipath in a wireless link. We also shown a possibility of a multi-user communication technique and has demonstrated the possibility of real-time data transmission. Regarding the future work, we have only focused on the vertical miniaturization of the spiral and did not focus on the radial miniaturization of it. So that can be one part in future we can consider. Second one is the axial ratio and the impedance at lowest frequency we have addressed, but we did not address the minimum gain at lowest frequency. So at low frequency, the spiral always have a very low gain. So how we can improve it, that we have to see. The balun we used is always placed outside the metallic cavity. So we have to see how we can integrate the balun inside the cavity. That is another one. For the tilted beam work, we are almost the first group who works on a tilted beam wideband spiral antenna. Okay, where we have almost a consistent tilt angle over a frequency band. But we don't have much control on the tilt angles, and we have to study more this kind of geometry. More importantly, we are using a spiral that can work between 2 to 18 gigahertz, but we are only observing the tilt between 3 to 6 gigahertz. So we are observing it over a narrow frequency band. So we have to see how can we increase the tilt angle of the antenna. In the last part, for the MDM section, we need to do further analysis, experiments, and analytical analysis, numerical analysis to understand the system or the working of the system in a better way. Also, we used a VNA, which should be replaced with a portable structure like an SDR or any small module to make the system completely end-to-end without a VNA. So I think these are the publications that we got based on our work in the thesis. We were able to publish in several international and national conferences, as well as in good journals, and also able to file some patents with the help of my co-workers. So now I would like to acknowledge a few people without whom this PhD was not at all possible. First one is Professor KJ Vinoy, who gave me an opportunity to work in one of the esteemed institutions, IISc. He selected me for PhD. He also considered me for this IISc UBO Thales CNRS project. So I have nothing else to say for him, but I was really influenced by his guidance, consistent technical inputs, and unbreakable patience, and obviously unrelenting encouragement towards the excellence. So next is Professor Cedric, who is my co-supervisor. He considered me to work in this lab, and he gave me everything that I needed to work in this lab. So he made an alternate home for me in France. Then Professor A. Chokalingam, who actually worked with us in the wireless system part, and he worked significantly and tirelessly in the theory part of the last work. Then obviously Dr. Noam Martin, who is the best friend of me in France. He was always around me and helped me everywhere. Obviously, Dr. Stephen Malagol, who was there whenever there is a technical problem. Even he did measurements on behalf of me, and he came and assisted me whenever it was required regarding any technical work. Mr. Christian Reynard from Thales, he also helped me to improve the manuscripts. Then the co-authors, I have a lot of co-authors who worked with big groups and have a lot of co-authors in each paper. So I would like to thank all of them who actually give a lot of input to improve the manuscript. The reviewers of the thesis, Professor KP Roy, Professor A. Mehta, and my supervisor and co-supervisor, and obviously the reviewers of my published manuscripts. I would also like to thank Microwave Laboratory in IISc and Labstick for giving all the facilities required for fabrication measurement, CNRS for conducting the joint collaboration between these institute, Government of India and Thales for providing me the necessary funding for research. Then all the chairmen in the EC department, the Department of UBO and CMI Brest for assisting us to stay quietly and work for our research in France. Mr. Srinivas Murthy, he is the person who handles EC office in a very smooth manner. Obviously, the hostel IISc and the international residence in Nelson Mandela, who gave me accommodation for whenever I needed. My teachers from all my schools, colleges, universities, who influenced me throughout the career and who are and will always remain a motivation for me throughout my life. Obviously, my parents, Dr. Ashim Kumar Ray and Mrs. Rita Ray, my wife, Paramita Shaha, and my all family members who allowed me to work for so long time away from home. So thank you, all of them. And at the end, obviously, my colleagues, some of them were sitting here, some of them are online, and some of them are they couldn't join. But I'm thankful to all of you who actually helped me to continue my work without any problem. And the last line I mentioned my colleague Ritesh Kumar, who will always remain a big inspiration for my life. So that was all about the presentation. Now I think I can address some of the questions or remarks that was given by the reviewers. First, there was a suggestion to remove some of the part in the preliminary chapters and to address some typos and mistakes. So I have corrected all of them and updated the manuscript and then submitted to the portal for updation. Then there was a question that why do we have significant differences between the simulation and measurement in some of the experiments? So first of all, we have carried out experiments with spiral several times, and with time we have experienced different. We have gained new experiences. So later, what we understood that it is important to cover the balun with a metallic casing. It is important to put an absorber inside that metallic casing. It is very important to give a cover in the cavity, to give a flash mounting arrangement. So in those experiments where were not able to do all this, we had some discrepancies. Another thing is we manually cut the balance, which actually sometimes reduce the strip width or length. When we reduce the strip width, we change the impedance. We have a variation in S11 magnitude. And when we reduce the length of it, we have a variation in the S11 ripples. So I think that's what happened during the assembly of the structure. From another reviewer, I got some points is what happens if we make an array of the spiral antenna? So it is a very interesting question. So I've simulated some of the one spiral antenna and plotted the patterns for different frequencies and for different array sizes. So here the beauty is if we have an array where the spirals are located at fixed locations, but as the frequency increases, the active regions of a spiral become small. So we are not changing any dimension in the array, but since the active regions are becoming small, with increasing frequency, the inter-element spacing increases for the spiral. So as the frequency increases, we start seeing side lobes. Okay, so that is the problem with a spiral antenna array for wideband application. There was one question that how can we reduce the mutual coupling of spiral array? Obviously, high impedance surface, meta surface are a possible solution for this kind of techniques which are already proposed. Or maybe we can use spirals with opposite winding, but in that case, I think one antenna can work as transmitter, another as receiver. Another thing, I thought that maybe we can use different heights, or we can put a metallic cavity wall. That's what I vaguely thought. In another thing is, can we apply the technology for curved antennas? So curl antenna is a development from a single arm spiral antenna, which was developed to feed the spiral and spiral geometry without a balun. So in curl antenna, it is an asymmetric geometry. So it has already a tilted pattern. And the problem is the tilt angle is not consistent with frequency. So for a curl antenna, the tilt angle goes at different directions for different frequencies. So obviously there is a scope of work is we may design a meta surface which will try to correct this movement of the beam and can guide all the beams in one direction. So to do so, we may need a spatial variation in the meta surface. In the last question, how do your work fit for a LEO constellation? So the LEO constellation is a constellation of low Earth orbit satellites, and obviously one satellite is not good enough to give a uninterrupted communication in low Earth orbit. So we need a constellation of multiple antennas. So if we consider one band between 10.7 to 14.5, I have selected some of the dimension. Is the maximum diameter of the antenna can be determined from the lowest frequency. So by doing so, we get a diameter of 8.9 mm. And obviously, the spacing between the antennas must be more than the diameter of the spiral. So I selected some of the values where it is possible to get an inter-element spacing between lambda by 2.6 and lambda by 1.4. So maybe we can make an array for KU band without having grating lobes. But there can be physical, practical, many problems which we can address later. Now, another thing is that for each antenna, we have to use metallic backing and absorbing material. And the last problem is to do a scanning with wideband spiral, it can be a challenging thing. Okay, so there I found only one paper in the scientific report where they have tried the same using a single arm spiral. But I'm not confident on an absolute solution of this, and this we can consider for a future work. So that was all about my work and including the questions asked by the reviewers. So if you have any questions, I think I'm open for it.
Yeah, so should I start, Professor Vinoy?
You can start. Otherwise, we can also ask the audience to start, and then you can maybe come back. Whichever way.
Okay, maybe then first audience can ask question if you have if they have any doubt.
So, anyone in the room, Aritra? Is there anyone in the room who want to ask any questions? You can maybe ask them.
Do you have any questions? Or I don't think from the audience right now we don't have any questions. So I request you to
consider. Online, anyone? Please open the unmute yourself, and you can ask if any of you have questions. All right, so maybe KP, back to you.
Okay, so very comprehensive presentation, and there was a clarity of thought in the presentation and very nicely summarized. I had gone through the thesis, and everything was covered in the presentation. So good work done. I have some minor queries and also some comments. The first one is you have used absorber,
yes.
To improve the performance at the lower frequency for the spiral antenna. So when you simulate, do you take the frequency variation of the absorption of the absorber in your simulation?
In simulation, most of the absorbers we used are typically given in the CST library, I used EcoSorb MCS, that has a frequency variation. that has a frequency variation, but I think the considered material doesn't have much variation. So so if your question is, did I consider frequency variation? Then yes, it is considered in the simulation.
So the loss tangent with respect to frequency was there with you for
Yes.
Various frequency.
Yes, sir.
Okay, so that you have incorporated.
Yes.
Okay. Now coming to lens antenna, very interesting.
KP, maybe I'll just clarify. I guess what Aritra said is that he has used the model that is available for N73 in CST. So it has some variation, but we can't be 100% sure whether that is what is, in practice it is. Yeah.
Okay.
Yes.
Okay. Yeah, I mean, I also guessed so. But some variation he has taken care of, so that's what it is defending. Okay. The second point is on lens antenna. You said that like you are getting the beam tilt at the higher frequency above 6 gigahertz, and at lower frequency there is no, that correct beam tilt. That's what you made presentation. What is the reason behind that you did not elaborate?
Yes, that's true. The thing is that at low frequency, we can. I thought of in this way that when we cover half of the antenna aperture with a dielectric or with a metasurface, and at the dielectric or metasurface almost have a flat response over 3 to 6 gigahertz band, or whichever band we considered. So it is like when the wavelength is longer, the phase change is smaller. So for the same permittivity compared to, so I just want to say that the phase and phase variation, especially the phase variation at low frequency, is smaller than the high frequency. So that was one reason I thought that at low frequency we have a lower tilt, and as the frequency increases, we have a higher tilt. And another problem was that above 6 or 8 gigahertz, the concentric ring becomes too small. So and there are also a possibility of higher order modes, which doesn't let us design the tilted beam accordingly. So that was the reason we just restricted ourselves between 3 to 6 gigahertz. Did I answer you?
Yeah. So did in your simulation, did you vary the thickness of the lens linearly? And because central portion will contribute to highest frequency, and the end portion will contribute to lowest frequency. So if you could have tried increasing the thickness of the lens linearly, when you move from the center to the end, probably you could have got better beam tilt at lower frequency, because you did modify the thickness of the lens, but then you are reducing the thickness. I saw a profile what you had presented. So you are reducing at the end. So probably, that linear tilt would have given you that linear thickness increase would have given you a better tilt at lower frequency. Do you think so?
Sir, actually, we have first we simulated the flat lens, then we simulated the exact structure that you just described. Okay, so in that we linearly increased the lens thickness with frequency, so maintaining the minimum height close to the high frequency and maximum height close to the low frequency. So that was the geometry we investigated, but we skipped here to make it coincide. But in that part, obviously, we got a better response compared to a flat absorber. But then we realize that that technique is not sufficient to get a response of what we are getting with this proposed geometry. And here the thing is that the lens is in the near field of the spiral. So this assumption that at low frequency we will get more phase. Obviously, at low frequency we will get more phase, but it is a near field interaction. So always the tilt may not be very consistent with frequency with changing height. So that is why we again switched from the geometry that you have just described to this kind of geometry that we have proposed.
Okay, okay. You also mentioned that real part of the dielectric constant was responsible for beam tilt, and that imaginary part was giving you flat beam tilt. This, I mean, that radiation, that amplitude. So, what is the basic physics behind that? Why? Because here the imaginary part represents a loss factor, isn't it?
Yes.
So, so is it getting damped because of that? You have constant that radiation, or but then that will get reflected into a reduction in radiation efficiency and thereby gain. So, how do you explain? I mean, your statement that I mean, imaginary.
Yes, I understand.
Yeah.
I understand. So it is a true concern that I try to address in a future work. But in my opinion, or from our understanding, the real part is producing a phase imbalance, whereas the imaginary part is producing a magnitude imbalance across the antenna aperture. So we were unable to address or to control these two imbalances independently, or to connect these imbalances directly with the tilt angle. So that is what we are unable to do in this work. Okay, so if we can somehow we can connect these imbalances with this imbalances magnitude and phase with these tilt angles, maybe we'll get some answer. But that is what I can all say about your question.
Okay. Okay. The last question, I mean, there was a question from other reviewer, about the array, this you have used, and then you have explained also nicely. You have did simulation and then try to show that there are, lobes that is getting formed at higher frequency. You did mention about grating lobe in some other context, but then there also, the explanation will become a little bit more sharper if you see from grating lobe point of view, because when you are increasing the frequency, then same physical distance will be multiple of the wavelength. And that doesn't satisfy the criteria of separation of grating lobe. So in this thing, some of these that radiation pattern, they are not side lobes, actually they are grating lobes, So I was looking for the answer there. Whatever you have replied, somewhere you should bring in the concept of grating lobe for the array at higher frequency.
Okay, thank you, sir, for this. I missed it. I missed this point, but you are correct, and thank you, sir, for this input.
Yeah. So otherwise, very good work. It has got direct application, and also it is required in our country. So maybe Professor Vinoy can start coordinating with ADA, because till now they import these antennas from South Africa. So, so it's a good work. I mean,
thank you, sir.
Yeah, and I really congratulate the what do you call the researcher. I mean, and also both the guides for this excellent work, which has got direct application. So that's from me, Professor Vinoy.
Thank you, and thanks for the comments. Cedric, any other point? Anybody from that side?
No, it's okay.
Okay. All right. So, do you have any other questions to be asked in private? Should I ask everyone to leave? Can we?
Oh, the last part I thought I'll mention to you, so that would.
Yeah, maybe we'll ask everybody to others to please sign off or leave the room. Only maybe for the moment, if Aritra can stay, everybody else please sign off. And Aritra and Cedric, I request to please stay.
Yes, yes. Just wait. Just 2 minutes. It will be good in 1 minute.
Yeah, keep.
Yeah, Vinoy, this there was a requirement, as I was mentioning, and we also tried making this antenna for EW application. So, and then TOT was transferred to HL, but then they could not reproduce that one. So with this new concept, of using metamaterial and then making it more compact, maybe this will find direct application for some of our indigenous requirements. So that can be, these things can be adopted if there is I mean, you can coordinate, and since it's a patented, these things, there should not be an issue, I believe. Was there any, was that application also kept in mind, Vinoy?
No, this actually Aritra's work was funded by Thales. Okay. And that is how his visit to France was also facilitated. Mm-hmm. The patent is on the that lens geometry that you saw. Okay. The metasurface metamaterial application into this was not included in the patent work, and that's actually done here. Whereas this work was done when he was at France in University of Brest in LabStick, which is the lab that Professor Quendo runs there.
Mm-hmm. Mm-hmm. It's a very good work, and then maybe some more number can be fabricated, and the repeatability can be checked, and then it can be directly used.
Yeah, we can explore that.
Yeah.
From the thesis perspective, anything should we ask Aritra to leave, or you want to just go ahead?
No, it's fine. I mean, that is fine. Like we have covered all the points.
Okay.
So,
Aritra, you can turn on the video also.
Okay.
You can turn off the presentation, but turn on the video. Yeah.
Mm-hmm.
Okay, so it's a good work.
Thank you, sir.
Okay, so with the examiner's permission, I would like to, congratulate you for the good work. And Cedric.
Yes, I would like just to share my feelings. So this adventure began in 2015 with Jean Chazela from Thales, and we meet together at this occasion, and we launch this huge program of PhD fellowship funded by Thales. But finally, 8 years later, only one PhD is only one PhD. So it was not easy because of intellectual property, financial problem, and so on. but finally with success. So I would like to thank Vinoy, Professor Vinoy, because you are alone in India. We are 3 in France.
Yeah.
So I would like to thank Stéphane Malégol and Noam Martin also. And a special thanks also to Srini Kaveri from CNRS, because he helped us a lot. I would like to have also kind words for Aritra, because this success is your success. Due to thanks to your scientific and human skills, because there is also a lot of problems, and you stay quiet, you stay cool, and all finish with this very good presentation. So your work is good, your presentation is good, and I would like to thank you and to congratulate you, because you can be proud of yourself. Thank you. Thank you.
And thanks, Cedric, for staying through a long time, And incidentally, we have another student from the department currently in, I think, another university right now. She has gone there last month or something. Yes. And so we hope that this program will continue. With me or without me, I don't mind. But then, at least there are new students. So we are continuing. And special thanks to my good friend Kefi for reviewing the thesis and giving the nice comments on the thesis.
Thank you.
So I will send a report on this maybe later today to Cedric to have a quick look at it, and after that I will send it across for signature using Adobe Sign. Maybe both of you can sign on it, and then we can proceed with that. Aritra, I have not seen your note use thing done through SAP. Is that you please follow up where it is if it is stuck.
Sure, sir.
Yeah. Okay. All the best again. Enjoy and
Thank you, sir.
Congratulations on the PhD. Yeah.
Thank you, everyone.
So we'll sign off now. Thanks everyone.
Okay. Bye.
It's done?
Yes, I thought there is a session without you, but
no, he asked for it, but the reviewer said that
it's not necessary. Okay.